Welcome to The Explainer. So glad you're here. We are diving into something absolutely massive today. If you're building, testing, or honestly just relying on AI right now, you know about the concept of LLM as a judge. It's standard practice, right? We use large language models to evaluate and rank the outputs of other models. We throw some outputs at it and expect a solid, objective, deterministic answer. But what if it's all an illusion? Researchers are calling it exactly that, the deterministic illusion. We're going to break down exactly why trusting an AI to give you the same evaluation twice is, well, a really dangerous statistical game.
Here's our roadmap for today. 1. The deterministic illusion. 2. Exposing statistical noise. 3. Why evaluation pipelines break. And 4. How to actually fix your judging workflows. Let's get right into it.
So I've got a question for you. Is your AI judge essentially just flipping a coin? Think about it. When you feed two model outputs into an LLM and ask, hey, which one is better, we instinctively expect a reasoned, logical choice. If it picks option A on Tuesday, it should absolutely pick option A on Wednesday. But as we're about to see, relying on a single pass from an AI judge might literally be as noisy as flipping a quarter to make your core engineering decisions. Section 1. The deterministic illusion, unpacking the archive study. Okay, to really understand the scale of this problem, we need to look at a fascinating recent archive study by Abel Yagubian. They put OpenAI's GPT-4o and GPT-4.1 Mini to the test across 29 different tasks. And here's the kicker. Instead of just asking the models once, they ran 50 pairwise and 50 pointwise trials per question to check for run-to-run reliability, just hitting reload on the exact same prompt over and over. And the result? 13.6%. Across the models tested, pairwise preferences, meaning it chose option A over option B, flipped an average of 13.6% of the time. The exact same question. Think about what that means for your evaluation pipeline. Nearly 14% of the time, the model contradicts its own previous judgment without you changing a single word of the input. It totally proves that single-run evaluations are just statistically unsafe. You aren't measuring model improvement, you're often just measuring sampling variance. And it gets wilder. Check out this massive flaw, a severe first-position bias. When testing the GPT-4o mini model, researchers found that it picked the very first option presented, option A, a staggering 72% of the time. That means if you literally just flip the order of the answers, keeping the text completely identical but making option B first, the judge is highly likely to change its mind based purely on formatting. It's an incredible bias that directly and artificially inflates scores for whatever model happens to get evaluated first. Let's dig a little deeper into those 50 trial reference runs, because the data completely shatters the myth of the reliable single-pass judge. 28% of the questions had a flip rate exceeding 20%. In extreme cases, one question hit a 56% inconsistency rate. That is literally worse than random chance. And get this, just making tiny semantically equivalent tweaks to the prompt's phrasing shifted the entire majority outcome a quarter of the time. Now, you might be thinking, well, I'll just use two different judges. Nope. Cross-judge agreement sits at just 76%, meaning two different AI models will completely disagree on nearly a quarter of all comparisons. The noise is baked right into the system. Section 2. Exposing statistical noise, the pairwise-pointwise gap. So, there's this really bizarre contradiction in how these models actually process quality. It's called the pairwise-pointwise gap. Basically, pairwise evaluation forces a binary winner. You force the model to say A is definitively better than B. But when you run a pointwise evaluation, where the model just grades each option out of 10 independently, you find that the actual scalar score gap between the two is tiny. We're talking just 0.19 to 0.36 points. In aggregate, those gaps aren't even statistically significant. The pairwise logic is essentially pulling a winner out of thin air, declaring a decisive victory when the model's own internal scoring admits there's practically no difference in quality at all. Section 3. Why evaluation pipelines break. Downstream consequences. Why does all this actually matter to you? Well, the cost of this illusion is severe. When you build on top of noisy feedback loops, everything downstream breaks. Public leaderboards, they become completely unreliable. You can't tell which open source model is actually winning. Reward model training loops get corrupted because you're training your AI on unstable, flip-flopping labels.
Internal A/B testing frameworks fail to separate actual improvements from random variance. And honestly, the worst part, downstream models just start optimizing for judge quirks, like desperately trying to format their output to look like an option A, instead of genuinely improving their capabilities. Which brings us to the defining takeaway from the source material. Single trial LLM judging is often too noisy for high stakes evaluation. It hits the nail on the head. If you are using an LLM as a judge to make product defining decisions, grade crucial outputs, or steer your model's training, you just can't afford to ask the judge once. We have to fundamentally change our approach. Section 4. Fixing your judging workflows. Concrete developer steps.
The good news? We aren't just here to complain about the problem, we are here to solve it. Here is your high-level roadmap to neutralize the bias. Step 1. Implement position randomization. Never, ever evaluate a fixed A-B order again. You must shuffle those prompt positions before every single judge call. Step 2. Aggregate across repeated trials. The single run is out. You need to compute a majority vote from multiple runs. And Step 3. Report uncertainty explicitly. Stop pretending there's always a definitive winner. Start returning confidence intervals and trial variance. Now let's talk math. 11. That is your new magic number. The reliability curve analysis in the study demonstrated that you need exactly 11 repeated trials of the identical prompt for a majority vote to accurately recover the 50-trial reference verdict with a 95% probability. Let that sink in. If you want 95% confidence that your AI judge is making the right call, you have to ask it 11 times. Let's get really tactical with your code implementation. You're going to want to write a loop to shuffle A/B prompt positions before every single API call. And while 1-1 is the standard, you should bump that up to 15 trials for tasks you know have high variance. Next, set up some guardrails. Reject decisions entirely if the confidence vote drops below 0.65 threshold, and flag them for human review. Also, decouple your logic. Use point-wise scoring for basic quality thresholding, and strictly save pairwise head-to-head only for relative ranking. Never mix them without statistical testing. Finally, validate everything across multiple model providers. The archive study focused heavily on OpenAI models, so run your judge evaluations with at least 2 different model families to make sure you aren't just capturing one specific provider's quirks. It really all boils down to this. Single-pass LLM judging is dead. The old deterministic evaluation pipeline is officially obsolete. Multi-trial aggregation and position randomization aren't just cute best practices anymore. They are absolute statistical necessities if you want your evaluations to actually mean anything at all. As we wrap up this explainer, I want to leave you with something to chew on while you head back to your code editors and architecture diagrams. If AI cannot reliably judge AI on the first try, without a massive team of statistical safeguards holding its hand, who is really keeping score? Are we actually evaluating the intelligence of our models, or are we just testing our own ability to filter out their noise? Thanks so much for joining me to unpack this fascinating data. Go implement those multi-trial loops, stay curious, and I'll catch you in the next explainer.